So it's my pleasure to introduce Theo Papazachariou from the University of Essex, who's speaking on K-moduli for log-Fano complete intersections.
Yeah, thank you. Thank you very much for that. As mentioned before, I'm going to be speaking on this topic of the K-moduli for log-Fano complete intersections. I'm very happy to do so, even we're still in an online format. I quite enjoyed the seminar. So just a quick plan of what I'm going to talk about today is a little bit brief of context on Fano varieties and why we want to study K-moduli. And then I want to describe a specific example of such a compactification of the K-moduli where we have a family of threefolds, which is given as blowups which along some complete intersection of quadrics. And then I will switch it up a little bit and I will talk about K-moduli spaces of log-Fano pairs. So these pairs that you see on your screen, this pair S1 minus beta D, where in the case we will discuss later on, this is going to be a Delpezzo surface of degree 4, so a complete intersection of two quadrics in P4. And D is going to be an anti-canonical divisor. And I will, maybe the name itself, while crossing, doesn't ring a bell, but I will try to explain a little bit how that works. And I will give an example in this particular case. And then if I have time, which I hope I do, I will talk a little bit about some other known results for K-moduli and what I think can be potentially done in the future based on recent advances. So just for the context, as I promised, we will work with smooth, unless stated otherwise, Fano varieties, and we will work over the complex numbers in this case. So if you're not familiar with these, then you can think of these as some projective varieties that have a positive Ricci curvature. So in the simplest of terms, like higher dimensional analogs of the sphere. In more algebraic geometric knowledge, we just say the anti-canonical line bundle is ample. And so historically, the way we study these Fano varieties is to try to classify them into some deformation families, which will depend on the dimension. And this is a good enough classification, although it's still ongoing, as I'm going to describe later on. So just a brief overview of this. In curves, you only have one family. This is a P1, and it's easily understood from the Fano varieties perspective. For surfaces, you have 10 families, and these were starting to be described and discovered even in the 19th century. So there's been a very rich background of studying these guys, and they were discovered by Pasquale Delpezzo. They're also known as Delpezzo surfaces for this reason. So these are given as blowups of P2 in n number of points, and n can be between 1 or 8. And also you have P2 and P1 cross P1 as the other two guys. So the degrees of these guys are is 9 minus n, where n is the number of blown up points, and the degree in this case you can think of as the self-intersection of the anti-canonical. So as I mentioned before, I mentioned this Delpezzo surface of degree 4, which I will denote by this dp4. This is the complete intersection of my bad, of two quadrics in P4. And this example is what gave motivation to the idea of this study in this talk. So for threefolds, you have 105 families. This was done by Iskowski, who classified some of them at the beginning of 1980, and then Moribukai in the 80s, which finished them. the classification of threefolds, final threefolds with higher Picard rank. And for fourfolds and above, the exact number of families is not known. We know examples of Fano varieties in dimension 4 and above, so Fano fourfolds and above, but we don't exactly know what their number is. But what we do know, when it's a strong result, is that their number is actually bounded. And this is, I think, a result by Kodaira, Miyaoka, and Mori in 1992. So this is a good enough classification, but due to recent advances, we know we can do more. So what we want to do, or what I personally want to do, and other people in the field want to do, is to compactify the moduli of these families, of this smooth manifolds. And we want to do this by creating a compact moduli space. So the way we do this, or the way we want to achieve this, is we want to add singular elements. So these deformation families will have like some limit elements. You can think of it like that. They will have singular points. And then we want to find a moduli space that has nice properties, compactness being one of them, that will allow us to compactify the moduli of these families. And if you're not familiar with modular spaces, these are essentially spaces that will parameterize objects with some common properties. In our case, usually some common algebraic geometric properties. So the question is how you can achieve the above. And it seems, and mainly due to recent advances, that the best way to do this is through case stability. So I won't go into like super much detail into what case stability is, and I won't like define too many things, but if you're unfamiliar with theory, you can think of it being a theory, an algebraic geometric theory, which was developed to answer which Fano varieties will emit a Keller-Einstein metric. And this is the famous result by Chen, Donaldson, and Soon from 2012, where if X is a smooth Fano variety, X will admit a Keller-Einstein metric if and only if X is K polystable. So this theorem and this seminal work from Chen, Donaldson, and Soon shows that if we want to find if something is admits a Keller-Einstein metric, then we have to look at this particular notion of stability. The interesting thing is that when we construct a space with this space M bar K, which is the space that will parameterize K polystable. I say pairs here because I will use pairs later, but K polystable varieties. This is in fact a compact modular space, and this was found by Li Wan and Xu in 2017. But the problem with this is that the construction of this modular space is not explicit. It's not enough for us to be able to describe what is in this space. So in particular examples, we really need to try to find out what we have to add in this space, in particular the singular elements that will lie in the boundary. And as such, since we know that this space has some of the nice properties, along with others like properness and so forth, and it's a projective space as well. This is a wealth of new results that come from a bunch of people. I don't want to name all of them because I'm certain I'm going to miss one of the names. But because we know that the space now has these nice properties, one of the aims that we can identify is to describe this space for different families. And it seems to be that the best candidate to do so is to use geometric invariant theory. And if you're familiar with this, geometric invariant theory is relatively old. I mean, it's not terribly old, but it was developed by Mumford in the 60s. It was based on Hilbert's invariant theory, and the main goal of this theory is to describe quotients of algebraic group actions on varieties, in our case, projective varieties. So we can think of an algebraic group G that will act on a scheme X, and we want a notion of something called a good quotient of polystable orbits. So in a way, we want to be able to define the quotient into a projective Euclid-Wish variety. So in a similar way, we will denote by this M bar GIT the modular space that parameterizes the GIT stable points. Again, the reason why we want to look at GIT is, first of all, K-stability has a lot of elements that come from GIT, but GIT is easier to describe explicitly because it has existed for longer, and there are better computational, if you wish, methods to describe this. And I'll describe this a little bit in the next example. So I promised an explicit conjunctification. So this is final threefold 225. So we will have C to be the complete intersection of two quadrics in P3. And you will notice that this is not a final variety, but if it is smooth, it is actually an elliptic curve. But if we blow up P3 along this curve, then this is a final three and just smooth final threefold in the family 225. And what is known is that if X is smooth, this also implies that C is smooth, which implies that, in fact, that X is K-stable. So if you want to reference for this, I will provide it later on when I discuss about future endeavors. There's a really nice book that describes the K-stability of and K-stability of a lot of final threefolds, and it has a wealth of results in this. But this is a relatively known result. But since we know this statement for this particular final threefold, which is smooth, the question is, what can we do in the singular cases? So as I mentioned before, we can study the GIT of the complete intersections of two quadrics in P3. And this has been done in part by Arbitrator Miranda in 1994, where they look at general GIT problems of intersection of two quadrics in a general ambient space, but through some computational methods, I've just provided a bit more of a geometric description to this. So this theorem is that the first part is from Arbitrator Miranda, that if this curve is smooth, then this is also GIT stable. And then I show that if this C tilde, which is a special curve, which is a quadrangle with 4 ordinary points, so 4 A1 singularities, you can kind of think of it like, my drawing skills are not great, by the way, but you can kind of think of it like this in P3. These are your 4 different A1 singularities, and this is going to be your curve. So in this case, you can show that this is the only strictly GIT polystable curve of this complete intersection. And then another extension is that if C has only at worst A1 singularities, so ordinary double points, then C is GIT semistable. And this is also an if and only if statement. So this gives a complete description of the GIT problem of the complete intersections, but then you might ask what is happening in the K-polar stability case. And the first lemma, and this is proved by a theorem of Pacharev for toric varieties, but the first lemma says that if you have this special X tilde, which is the blow up of this special C tilde, so this quadrangle along P3, then this is in fact K polystable. So I will denote by M bar K X to be the K modular space which parameterizes the K polystable blow-ups of a complete intersection of two quadrics in P3, and then I will use this notation here for the M bar GIT 322, which will be the GIT modular space, or the GIT quotient, if you will, which parameterizes GIT polystable complete intersections. And then my theorem is that, in fact, there exists an isomorphism between these two modular spaces. And in fact, I think I show that this exists on the level of stacks, which I don't really want to get into. But the idea here is that these two spaces are pretty much the same. And the usefulness for having such a statement is we know exactly what the GIT classification is here. So we can pretty much exactly say what needs to be included in this K modular space, this M bar KX, which parameterizes the K polystable guys, because we have a good understanding of the GIT problem. So the way this theorem is proved, it uses something I call the reverse moduli continuity method. And this is based on the original modular continuity method, which has appeared in many authors, but I think it's originally from Odaka, Spotty, and Soon, which studied similar homeomorphisms between K modular spaces and GIT spaces for delta surfaces. And in fact, it's a powerful method because you can relate these K modular and GIT modular spaces even up to an isomorphism. So that's all good and everything, and it's a nice result. But then I think it's interesting to consider the case of pairs, because in the case of pairs, one can show that you can take it, you can have even more interesting geometric results. So remember, we said that we had a group G that was acting on a variety X, and without going into huge detail on the GIT side of things, if the dimension of the Picard group is 2, then what happens in the GIT quotient is that the stability conditions will tessellate with respect to some parameter T. And this parameter T is in fact given by a line bundle of X. So what this means is that, and this what you're getting is what is called a wall chamber decomposition and the wall crossing phenomena that I mentioned at the beginning of the talk. What this means is that if you have different T's, so let's say this T and T prime, the two moduli spaces, just the two GIT quotients, if you will, M bar GIT T and M bar GIT T prime here, will be isomorphic if and only if either T equals to T prime and they are on the same wall, or T and T prime belong in the same stability interval. So you can kind of think of it like as a line. The first one is that they're both the same point here, and the other one is that you have a wall here, you have a wall here, and then this is your T, and this is your, this is your T, and this is your T prime. And it's interesting because as this parameter changes, the stability conditions will change a lot. So what does this have to do with log Fano pairs? Where in fact, if you have log Fano pairs of this form, so these log Fano pairs will have a variety S, projective variety S, a divisor D, and a rational beta, so S1 minus beta D. And we want the whole line bundle here to be ample. You actually get a similar wall chamber decomposition on the K modular space. So in fact, this K modular space that we described before, this M bar K, will depend on the parameter beta and will also the stability conditions with tessellate with this parameter. And the interesting thing here is that variety in the divisor will both be deformed before and after the wall. And this is why getting explicit examples in K moduli, and this what I mentioned before, the wall crossing, so this particular how the formation between the previous wall and the next wall are interesting geometrically to obtain, but unfortunately they're very hard to describe explicitly. similar to what we did before with family to 25. These kind of things are harder because you're adding a level of complexity, and it is just harder, but it can be more interesting geometrically, at least. So I want to study such examples of world processings. In fact, I will give you an example in a little bit, but I will give a bit of the necessary theory that's needed to construct such an explicit example. So I'm going back to the case of pairs. I don't want to consider log Fano pairs for now, just pairs of a variety and another variety. Here, S will be a complete intersection of K degree D hypersurfaces in Pn. So you can think of S being F1 up to Fk, where all of these Fi are degree D, and H will be a hyperplane. So the GIT of these pairs is variational, and the reason for this is that the parameterizing space in this case is a Grassmannian times Vn, and the overall dimension of the Picard group, the overall dimension of the Picard group is 2. So it lies in the description I mentioned before. So when we want to study these pairs, we will get into what we discussed before, which is variational GIT, where we will have this wall-chamber decomposition and this tessellation based on a parameter. And in this case, a general line bundle here will be isomorphic to O of AB, and T will be given by B over A. So in general, I will denote this GIT quotient or GIT modular space by M bar GIT and KD with the dependence on T, because as we said before, this will depend on T depending on which wall or chamber we're at. So when we're studying these things, and as I mentioned before, it's incentive for us to study the GIT of things, the GIT side of things, because we can get explicit descriptions of these quotients. In order to do so, one of the most easiest in quotations, but fruitful ways to do so is to do so computationally. And there has been much development in the computational tools of these kind of things. And this is just my contribution to the specific case of these kind of pairs. So the first thing one can show is that, in fact, we already know that there exists a finite, the number of walls is finite, this known result, but the fact is that there exists a finite superset of walls that can be found computationally and depends only on N, K, and D. And what this superset means is that you can computationally find a finite set of potential walls where you know that the actual set of walls will be included in it. And this is going to be a finite set. So this means that you can computationally find it. So then if you perform some other tests, then that implies that you can find all the walls and the chambers. So in the case where N is greater or equal than K times D, so this is what would imply that your S will be a Fano variety, then because its line bundle would be ample, its anti-canonical line bundle would be ample, then this space we described before, this M bar, GIT, and KD, it will in fact parameterize pairs where S is our normal guy, our normal complete intersection, but D will be the intersection of S and H. So the interesting thing here is that D is a divisor of S, and it will give us benefits and incentives when we discuss the case stability, the case stability of log Fano pairs later on. So what this shows is that if you want to study pairs of the form S and D, where D is a variety of a divisor, and you know that D is a hyperplane section, then you can study the GIT, the variational GIT problem of your variety, but your hyperplane, and your hyperplane section, which would be more complex. So what I did was I actually developed an algorithm which will study the variational GIT picture. So using these two things and a couple of other more specific variational GIT tools, I can computationally find all wells and all chambers, but also all non-stable and all unstable families for each well, and potential polystable orbits for each well and chamber. So what this means is that if you have a good idea of what you want to study, the theory behind what you want to study, you can take this pretty mature classification, if you will, and then use geometric information to obtain the whole variational GIT picture. So obtaining the different variational GIT quotients, because you can kind of reconstruct the stable and non-stable and polystable elements from the unstable and non-stable elements. So as I mentioned before, I'm going to go directly to the specific example of S being the Duplex surface. So this is a complete intersection of two quadrics in B4. Sorry, a Duplex surface of B4, if you will, and then D will be the hyperplane section, which in this case is an anti-canonical divisor. And this is helpful in the case of the case stability, because the case stability of such log fauna pairs is better understood, if you will. So the first step in my research is to use the algorithm I described before, and then use the method and process it. I mentioned by using singularity theory to describe this M-bar GIT 442. So here in our case, N is 4, K is 2, and also D is 2, which is why I denote this by MGIT 422, depending on T, obviously, as I mentioned before. So let's kind of study what possible relation to K moduli this thing has. So as I mentioned before, S is a Duplex surface of degree 4, D is a hyperplane section, but in this case, D is an anti-canonical divisor, or it belongs in the linear system of the anti-canonical divisor. And so this minus KS minus 1 minus beta D, this is just, you think about it, this guy, or equivalent to this guy, which is minus beta KS, which is ample, just because KS is ample. So we want to study pairs like this, and as I mentioned before, if you want to find compact moduli, we want to do the K moduli. So we will denote the K moduli space by this M bar K422 beta, for similar reasons why we denoted it in the GAT case. The interesting thing is that these spaces, they have a natural line bundle, which is called the CM line bundle, the Chow-Mumford line bundle, and this has been shown to be ample. In any case, it was conjectured for a while. I would say that if it is or isn't projective, because an ample line bundle, because this would imply that the K moduli space was projective, and this was proven. But in this particular case of these pairs, of these log fauna pairs, you can actually compute the CM, what the CM line bundle would be, or show actually what it would be. And then the interesting thing is that you can find a relationship between the two parameters, parameter T and parameter beta. So in this case, the CM line bundle will be ample. And in fact, it will be isomorphic to this O of A of beta and B of beta. And this should be the other way around, sorry. And in particular, you can actually show that the parameter T, which comes from the variational GIT side, will actually depend on these guys. And in this particular case, where, remember, n equals 4, d equals 2, and k equals 2, you can actually find this relationship. And it is this. So T of beta will be 6 times 1 minus beta over 6 minus beta. Another interesting thing is that you can generalize this result for an arbitrary number of n, d, and k, where your d, your for your hyperplane section. So I actually did this, and the reason I haven't presented this here is just like a really horrible expression, but it is still doable, and it's interesting because it shows that kind of relationship between the parameter T and the parameter beta. And this came as an idea because it wanted to generalize a theorem in Gallardo, Martinez Garcia, and Spotty in 2018, which was done for k equals 1. So for the case k equals 1, this is the case where you only have hypersurfaces. So this is a bit more complex. And I should say now that a lot of the variational GIT stuff also generalizes Gallardo, Martinez Garcia, who did a similar computational method for these hypersurfaces, for k equals 1, which is, again, is a bit of a simpler example, but still quite interesting. So the main theorem and the main idea of what I promised, this explicit description of the wall crossing, is that if beta is greater than 3 over 4, you actually have an isomorphism between the two moduli spaces. So between the k moduli space here and the GIT quotient or GIT moduli space here. Similar to what we described before for 225, but this is a bit of a more interesting example because it happens for up to a specific number of beta, and also for log pairs and pairs respectively. But also, if beta is 6 over 7 is where you have the first wall crossing. So in fact, this isomorphism exists up to the second wall without the second wall included. So you know that the first and second chambers are going to be isomorphic, but also the first wall is going to be isomorphic. When I say the first wall, I'm not including t equals 0 because t equals 0 is the general, just the case of the hypersurface. So just the case of the not hypersurface, just the case of the Del-Pezzo surface of degree 4. And this has already been studied. So this is the 0th wall, t equals, let me say this more clearly, t equals 0 is the 0th wall. Then I think t equals a 6th is the first wall, which corresponds to beta equals 6 over 7. But the interesting thing is the variational GIT algorithm and just the knowledge of the Del-Pezzo surface, the singularities, and so forth will give you a description of these, of the guy here, the right-hand side, so the GIT quotient, and then you can exactly, not only predict, but you can say because of the isomorphism, what do you need to include in the K moduli side. So what happens is that if beta is greater than 6 over 7, so this is going to be the first chamber, then you either have, for the stable points, that S will be smooth, or have at worst D4 singularities, and then that S has at worst A1 singularities, but then D has also at worst A1 singularities. And the polystable points in this case is a very particular point. It's a pair that it will denote by this S tilde D tilde, where this S tilde will have again 4 A1 singularities, and D tilde will have 4 A1 singularities. And in fact, the interesting thing here is that this D tilde is the GIT polystable guy we studied in the previous example. So this is just a quadrangle, and in fact, this pair will appear as a K polystable pair for each Wallen chamber. Such an interesting geometric fact. So what is happening at the beta equals 6/7 wall is that the stable points, or the K stable pairs, if you will happen either if S will be smooth, or if D has at worst D4 singularities. So this point remains, but what changes here is that now S is allowed to have at worst A2 singularities, and D can have at worst A3 singularities. And then for the polystable points, we still have the pair, as I mentioned before, the special pair S tilde D tilde, these pairs with 4 A1 singularities. But the interesting thing is that we also include another pair here where S will have at worst A2 singularities. In fact, it will usually have A1 and A2 singularities, and D will have D4 singularities. And D will kind of look like this. Will be, you can think of it being as a conic and two lines matching at a point here. And as I mentioned before, it can either be this special pair that we described before, the pair S tilde 1 minus beta D tilde. So you can kind of see like this deformation very explicitly. This how this happens. You have you're kind of losing a stable point, and you're including an extra polystable point, which wasn't allowed here because the singularities of S start to be allowed to getting worse for to be included in the K moduli, but then you have to restrict the singularities of D. You can see this again in the range of 3/4 and 6/7, which is the second case, the K chamber or GIT chamber. It doesn't matter in this case because we know they're the same. So then the stable points will be that S will be smooth and D will have at worst D4 singularities. This is kind of everywhere, but in this case, D can have can have at worst A2 singularities, and D can have at worst A3 singularities. But the only polystable point is this pair here. In fact, this pair for the GIT chambers, at least from the VGIT side of things, this pair is the only GIT strictly polystable point in the quotient in every case in the chambers. And when you reach a wall, you'll have to include another point. So as I mentioned before, this kind of like deformation is pretty I wouldn't say clear, but it's evident because you can explicitly see it in this case. You can see, okay, you have some points that remain the same as these guys, but then you start to introduce points where S will have worse and worse singularities, and D will have better and better singularities. And this explicit description is quite nice, especially for the case of the divisors, because you can actually draw them and map them out and see what they are, because of the wealth of knowledge on the singularities of these guys. If you think about it, D is is actually a complete intersection of two quadrics in P3, and such intersections are known since the 19th century. So the method of how to prove this main theorem and then obviously obtain all this classification, this uses the moduli continuity method for log pairs, which appeared in Gallardo, Martinez Garcia, and Spotty in 2018. And the basic idea of this method, just to give you an understanding, is that if you have this relationship between the CM line bundle and you also have a couple conditions, then you can define a map between these two spaces, and topological properties and properties of stacks and the properties of the spaces themselves, mainly properness, compactness, and so forth, will give rise to an isomorphism. You'll need to be careful to know a couple of conditions on the geometry of things, but at least for the cases of pairs of such dimensions, this is relatively okay to do. So for some more known results, some results that exist in the literature, I kind of mentioned this before somewhere in the talk, but for Delpezzo surfaces, the families of Delpezzo surfaces, at least the ones that we know admit modular spaces, they were compactified in compact modular spaces by Odaka, Spotty, and Soon in 2012. I mentioned the modular continuity method before. It was one of the main ways to do so. And this was a quite nice result, and it expanded some already known results for some of the families. So the case of the Delpezzo, the Delpezzo surfaces of degree 4, this was already studied by Mabuchi and Mukai in 1994, obviously without using case stability because the theory wasn't fully developed yet, but through other methods, which I don't want to get into too much detail now, but this was essentially achieved in 2012 by Odaka, Spotty, and Soon. But the fact is that for threefolds, less is known. So Spotty and Soon, they gave an explicit compactification of the K modular space of Delpezzo quartic varieties. So the Delpezzo quartic varieties are a complete intersection of two quadrics in a general Pn. They showed it for n bigger than 4, shouldn't be bigger or equal. And the way they did this was essentially through case stability and GIT. So they found that they can relate the K moduli and the GIT moduli space through homomorphism and using similar methods to what was described here. And this is quite a nice result because it works in every n really, which is quite remarkable. And Liu and Xu in 2019 did the explicit compactification of cubic threefolds, also again using GIT. And then Liu, a year later, I think, also did the explicit compactification of cubic fourfolds. And there's a conjecture that you can obtain a result similar to Spotty Soon for a cubic n-folds, but it's open. But it's an interesting thing to think. But again, all these things use GIT, and the other known example is the one that we described today is that these blow-ups of P3 along a complete intersection of two quadrics in P3. These either smooth elliptic curves or singular curves that we saw before, these quadrangles and everything. And for the future, because there seems to be a trend that we're starting to study more and more of these things. One of the really nice results that I mentioned beforehand, and I said I would give you the name later on for a reference for why the smooth final threefold in family 25 is K stable is in this work by Araujo, Castravet, Chelsov, Fujita, Martinez Garcia, Shramotsus, Viswanathan. I'm sorry if I've forgotten someone, too many names. So this was last year, I think, and they pretty much described which of these final threefold families will contain K polystable elements. I think there are roughly 60 families that they should, and this essentially shows us which of these families will emit compact K moduli. So if we expect to be able to describe kind of like the methodology presented here and the ideas presented here, and the modular continuity method, the reverse modular continuity method, the relationship between the GIT quotients to actually describe these K moduli in the rest of the families. It shouldn't be 78 here, by the way. It should be around 60. I don't remember the exact number. I'm sorry. And some people I know are kind of working on this, but another direction would be to study log K moduli in log final threefolds, describe wall crossings. But I suspect that this is going to be a harder endeavor for final threefolds, unless if some more theories developed in order to how to find K polystable singular elements of log final pairs. But obviously this is an interesting and exciting direction in research, because this holds a lot of interesting geometric information, really. So yeah, this is all I want to discuss. Thank you very much.
Thank you. Okay, we have some time for questions, because you understand quite better than myself. So do we have any questions or comments? Okay, I have a question. So you claim towards the end that you can study log K moduli for non-example, for known example. Okay, given by known examples in threefolds to describe wall crossings. So you were pretty lucky in the, if you don't mind me saying it.
No.
In the example you got to hit one wall via GIT walls. Have you thought of maybe which examples may be lucky examples as well for threefolds? So do you have an intuition?
I don't have an explicit example, but I think I'm starting to get an intuition into why these things will probably happen, and I kind of think you need a high enough degree in order to be able to achieve that.
High degree, like anti-canonical degree, or?
Yeah. Like I think you need something like this. It's a 5. Sorry. Like minus kx, like the self-intersection of minus kx to be greater than about 25, I think. But this is based on a hunch and something that I want to look into more, but not something really concrete to be able to tell you.
Because of the let's say Liu Fujita bound that you use in the singularities. Yes.
Yeah, because even forget about log K moduli, like even if it's quite remarkable that these results exist the way they exist, because they can find what these singularities of the bounds are quite nicely without having to rely a lot on the bound. But yeah, this, at least for now, right? Maybe if more is understood on this thing, then you can drop this condition.
Okay, any more questions, comments?
Yeah, I have a question.
Yes, please.
Maybe you said it, but maybe I didn't heard it. Do you have any information about the Kodaira dimensions of these modular spaces, or for some of them at least?
No, personally, no. This is an interesting question because I think it's kind of like the next step of when we study these things. When I say we study these things, we find the isomorphism and it's nice, but then an interesting thing is to actually start asking what the geometry behind all these modular spaces are. So for this 225, I think we can safely assume that this is a P1, maybe mod some group action like Z mod 3 or something like that. But in general, I don't really know, to be honest with you.
If I may, I suspect unirational at least. I don't have a particular strong reason or even proof idea, but something tells me that they are not far from being rational. Any more questions, comments?
Just a quick comment on the previous question. For these particular cases, so for this guy, at least I know what the dimension is, because we can compute the dimension in the GIT modular space, but not that much more really. Sorry.
Okay, so maybe we leave it here. Thank you very much.
Thank you.
So thank you, everyone. Bye bye. Thanks, Theo.
Goodbye.
Bye.